So I'm going to be talking about a high gradient non-local model that incorporates dilatancy. And by dilatancy, so first of all, I want to dispel any confusion between what suspensions people mean by dilatancy and what granular, what it connotes in the granular flow context. It is not shear thickening. So dilatancy is actually an increase in volume, as the dictionary will tell you, a reduction in density. And so whenever you shear grains, the density decreases. The material moves away from the regions where it shears. Now the problem is that most of the models that exist do not capture that fundamental effect, which goes back to Reynolds, who discovered this in 1778, I believe. Most of the work I'm going to present to you have been done by my two students, Krishna Raj and Peter, but there's some other older work that I'm going to show you. I'm sorry, some of the colors don't appear quite well over here. Can you see this? Yeah. Yeah. All right. So if you can just about see this, well, I don't know. I can see it perfectly well over here. So let me start with what the deficiencies of the classical theories are. So the classical plasticity theories. Now, first of all, I'm going to be talking about really slow flows. So the limit of zero particle inertia, okay, and therefore the inertia number that Jean-Noël and others mentioned is very close to zero or very small, much smaller than unity. Okay, this corresponds to the Stokes flow regime in suspensions or fluid flows. So the particle inertia is unimportant. You can take particle density and set it to zero, and that is an important regime because it occurs in many practically relevant flows, like flows through hoppers or bins, which are extremely important in handling of grains. Now, so in this limit, one has to satisfy a yield condition for the material to deform. Okay, so and the yield condition is just this extension of a block sliding over a surface. You have to impart a minimum shear force in order, so that the block slides, and that shear force is just a constant times the normal force. And so essentially it's a tensor equivalent of this relation, that the shear force exceeds a certain quantity. And in addition, if you want to compute the kinematics, you need to relate the deformation, rate of deformation or the strain rate to the stress. Now, Joe talked quite a bit about theories where one ensures positive dissipation, where there's I think he called, what I forget the potential that he, dissipation potential that he was talking about, where the force here is the stress, and he related the stress to the strain rate. But in practice, or rather historically, in soil mechanics and granular mechanics, people have done it the other way around. They've related the strain rate to the stress. But it's an equivalent, exactly equivalent process, okay? And all the axioms that Joe required are necessary over here. As long as you have a potential that satisfies a positive dissipation, then you have a good theory. I mean, or that's the basic requirement of the theory. Now, this factor is called the fluidity that determines how well a material deforms when you apply when you get past the yield stress. So this is just the representation of the yield condition in principal stress space, and now since it is a scalar relation, all the quantities that appear have to be scalar invariant of the stress tensor. Okay. Now the nice thing is, if you use a simple enough yield condition, you can invert these two and get in a stress explicit relation for the constitutive relation, and that looks similar to the Newtonian constitutive relation, except that the viscosity varies as inverse of the scalar invariant of the deformation rate. Okay, so this satisfies rate independence, which you often observe in granular flows. If If you double the stress, the strain rate does not double. It remains almost the same. Now, that's one fundamental requirement for the very low inertia limit. But this very simple theory has major drawbacks, although it's been widely used. One of the drawbacks is if you apply this to a really simple flow, like shear between two parallel plates, then the strain rate is, or the velocity profile is indeterminate. And that's simply because the stress is rate indeterminate. Okay, you're dividing a strain rate by its scalar invariant, and in a simple shear flow like this, the scalar invariant is the strain rate. So you can't, so there's a indeterminacy of the kinematics. There's a more fundamental problem, and that's what my talk is about. This theory does not tell you that the material is going to dilate. I'm sorry, you can't see the colors here, but this is a region, so this is the region close to the inner cylinder. So we're looking at a cylindrical quid device. You're rotating the inner cylinder. The region close to the inner cylinder is where the material is shearing, and there's a lower density. So the grains are pushed away from that region, and the simple theory doesn't capture that. So, well, how about the extensions of this theory, such as the mu of I model that several people have talked about? I here is a measure of the grain inertia. Okay, so given a stress scale, this is the inertial stress, the fraction of the whatever you impose, let's call that P, and the inertial stress that would come about if the grains were just colliding against each other is the inertia, is the so-called inertia number. Stuart Savage was the first to have, actually this is the square root of this is the inertia number. What I've written here is what's called the Savage number, which Stuart Savage first wrote down in 1984. Now, so it's a very simple extension of what I showed you in my previous slide. You now set the friction coefficient to be a function of the inertia number. Okay, and there's a lot of experimental evidence where this seems to agree with a variety of flows, mostly simple shear flows. Okay, in other words, viscometric flows, but the flow is in one direction and the gradient is in an orthogonal direction. Most of the experiments are of that kind, and they find that all the data collapses into one curve that relates mu to I, and another where the volume fraction is related to I. Now, clearly this can't work in the limit of 0I, as I just showed you. Okay, the limit I going to 0, this tells you that the volume fraction is fixed, and that's not true. That's not what you observe in an experiment. So, what are the other problems with classical plasticity? Now, this is something that Joe mentioned quite a bit, talked about. It's Hadamard ill-posed. In other words, you impose perturbations on the system, and you take the wavelength of the perturbations to 0. The growth rate grows as the inverse of the wavelength to the power of 4. Okay, so the system is exploding. The instability is exploding, unlike any other fluid instability, where the wavelength typically grows as k squared, where k is the wave number, as k goes to 0. Here, as k goes to infinity, it's the growth rate goes as k to the power 4. So it's ill-posed, except in the narrow range of parameter space. Now, compressibility slightly alleviates the problem. Okay, so the mu of I model that I showed you had no compressibility. So assume the material to be incompressible, but it requires an unreasonably large bulk viscosity for it to be, for it to have any effect at all. It doesn't completely resolve the ill-posedness. It just makes it less of a problem, but it's not a practical solution. So now there are some extensions of classical plasticity. I'm going to very quickly walk you through these two extensions. One is Kosterow plasticity, which I dabbled in with my colleague Kosterow about 10 years ago or a little more, and that has to do with enforcing the angular momentum balance, which is normally taken to be implicitly enforced if the stress tensor is symmetric and there are no couples acting, no coupled stresses acting in your system, no torques acting on your particles, it's implicitly enforced. But when you have grain friction, then you have to worry about enforcing the angular momentum balance. Okay? What happens is, you like the Cauchy stress, you get an equivalent called coupled stress, and this is just one of the polar continua models, and you can have an asymmetry in the Cauchy stress. Now, so you take the simplest extension of classical plasticity, wherein you put in the coupled stress in your yield condition, and you extend the flow rule to take account of the particle spin, and the particle spin can now deviate from the vorticity. So in a fluid, the mean molecular spin is the vorticity. Over here, the two can deviate. Those are the two key differences between a normal continuum and a polar or Kosterow continuum. One is the kinematic variable, which can differ from the vorticity, and another is the coupled stress, the dynamic variable. So now, if you take the simplest possible extension, I don't think you don't need to know the details over here. It's the simplest extension of your classical plasticity, and magically it seems to work. So first of all, it solves the problem of kinematic indeterminacy. Okay, you can compute the velocity profile in a simple shear flow or a more complex flow, and you typically get this exponentially decaying velocity as you move away from the moving surface. Okay, and there's experimental data for this. So the red dots are the experimental data, the blue line is the theory. And now, if you start making the walls rougher and rougher, the shear layer thickness, the thickness of this exponentially, or rather the length scale that comes from the exponential decay of the velocity, increases as you make the walls rougher and rougher, or as you increase the system size. Okay, so this is the shear layer thickness in terms of the particle diameter versus the system size. So this is flow in a channel. So as you make the channel wider and wider, the shear layer thickness keeps increasing. It's not a constant multiple of the particle size. Now, so there's a little bit more evidence for this Kosterow plasticity, although in the end I'm going to abandon this. And now here we did the experiments of aluminum discs going through a very narrow hopper, or rather a small angle hopper, and measured both the particle spin, and from the mean motion we could get the vorticity, right? So, and for a hopper, they are of different signs. They're not just slightly different. The vorticity is positive and the mean particle spin is negative. Okay, so we were quite excited. But then since then, there have been no measurements of the other important element of the Kosterow theory, namely the asymmetry in the Cauchy stress. All molecular dynamics or particle dynamic simulations seem to indicate that the stress is symmetric. And the other important shortcoming of this theory is that it too does not predict or incorporate constant pressure dilation. Okay, so that's something we abandoned a while ago. But the reason I go through this is because some of the elements of the theory are going to be related to or useful in what I'm going to formulate at the end. So the next second theory, please tell me, can you tell me about 20 minutes beforehand? Okay. So there was a non-local fluidity model proposed by Ken Cameron at MIT and his co-workers, where he proposed that this fluidity that I introduced a few slides ago is not a local quantity, it diffuses, or it can diffuse. And he wrote down this balance for the fluidity. It's just a simple diffusion equation. Now, he sort of got this in analogy from a model that was proposed for emulsions, which was supposed to be a thermal emulsion. So it had some thermal motion where one could make an argument for this kind of theory. I don't see how it could be applicable to overdamped, totally dissipative systems such as frictional grains, frictional elastic granular materials. But the interesting thing is he does get the same kind of exponential velocity decay. All theories that work give you this exponential decay. So that's the signature. The other shortcoming is, apart from the fact that you have to pull out this theory, unless he makes the evolution equation for the fluidity time dependent, so it has to be a time dependent evolution equation, it too is Hadamard posed. And thirdly, fourthly, the most important shortcoming is that it also does not incorporate constant pressure dilatancy. Now, so I've been going on and on about constant pressure dilatancy. So why is it important? So I'll spend a few slides on that to first, I think, convince you that it is an important effect to include. We came upon this not by looking for a theory that needed constant pressure dilatancy, but by doing an experiment that suggested to us that this was something we should think about. And the experiment was a rheological measurement of say glass beads in a cylindrical cuvette device, and we normally done, but by measuring the stress as a function of position. Okay, so we could measure all components of the traction on the outer cylinder as a function of depth from the free surface. Okay. Now, suppose the material was static, suppose you were not rotating the inner cylinder, then you get this kind of saturation of the stress, and this is the well-known Janssen saturation that simply comes from the fact that the outer cylinder or the boundaries are holding up a part of the weight by friction, which doesn't happen in a fluid. Right? In a fluid, the pressure would simply rise linearly with depth, but over here, since the wall is holding up a part of the weight, the pressure or the normal stress saturates, and so does the shear stress, the vertical shear stress. Okay. Now, if you now start shearing, something really remarkable happened when we conducted the experiment, and this was in these two papers. All components of the stress, the magnitudes increase exponentially with depth. Okay, and the shear stress changed sign. I mean the vertical shear stress on the outer cylinder. So it was positive initially, and the moment we started shearing it, it changed sign. Okay, and at that time we had no idea what the reasons were for this. We had a few hypotheses. So we were trying to understand how one could figure this out. And 20 minutes, great. Okay, I think I'm doing fine. And to figure this out, we did some more experiments. We did imaging from the top, and then we conducted particle dynamic simulations, DEM. Essentially, these are spring dashpot models that define particle interactions. So the interactions are dissipative, there's friction, and there's elastic restoring force. I won't go into the details. So these are the imaging experiments, and this actually gives away part of the story. If you look closely, you can see that the grains are not just moving in the azimuthal direction, okay? But there is a radial velocity, inward velocity. And then if you go to if you look at the simulations, I'm really sorry, the colors are not showing up at all, but you can see the streamlines. Okay, you get a nice single system spanning vortex. Okay, that's an animation that shows you the same thing. All the other particles are made transparent, so you only see these two layers, but it's a full system full of particles. You can see that the secondary vortex and all velocity components decay exponentially from the inner cylinder. Okay, and it's this kind of vortex is very similar, secondary flow. By the way, it's secondary because it's not as though I need to cross a critical parameter to get this flow. It always happens. Okay, so it's not a secondary flow in that sense. It's not caused by an instability. It's always there. So it's very different in that sense. And secondly, it's not centrifugally driven. It's not inertially driven. So, what's the use of knowing that there's a vortex? Well, the fact that I know there's a vortex, now if I go back to my simplest plain vanilla plasticity theories, I can now explain the exponentially the change in sign of the vertical shear stress and the exponentially growing stress components. So all I needed to know was that the velocity in the z direction varies, has a positive slope with respect to r. Okay, dvz by dr is positive. That's all I needed to know. So, but the plain vanilla theory does not predict this secondary flow, of course. Okay, so the question is, what will, or what is required? What are the ingredients required to now get towards predicting the secondary flow? So I have to first answer the question, what causes the secondary flow? And this tells you that it's not the centrifugal force, because if I do the same experiment between two parallel plates where there's no centrifugal force, I still get the secondary vortex. Okay, so secondary again within quotes. And so what finally gave us the answer was looking at the early time behavior. So when we just started the shear, what you can see is particles move away from the inner cylinder. So the left hand side is the inner cylinder, the right hand side is the outer cylinder. The color bars indicate the speed, the logarithm of the speed of the particles in the RZ plane. Okay, so you're looking at a cross section. So at early time, particles move away, but then they hit this wall here, and the only way they can complete the circuit is to move up and then roll down again. So at long time, you see this inclined free surface. So particles rolling down this free surface into this low density region and then going back up. So it's dilatancy. I mean, that particles move away from the shear layer because of dilatancy. They have to reduce the density there. And that's the reason I kept going on about theories having to capture constant pressure dilatancy. Constant pressure because initially the pressure at any given depth does not depend on radius or the radial position. Okay? So you have the pressure at constant density can cause a change in, at constant density you can get a variation in the density. Okay? So, yeah, so you can have dilatancy at constant pressure. So now that's the density profile. So you can't see the color, you can't see it from here, but perhaps you can see this plot, and it shows you that near the inner cylinder there's a much larger width of the lower density region than near the outer cylinder, and near the outer cylinder the material is static. So whatever depletion you see over here of grains is because of the way you filled it. Okay, you cannot avoid depletion of grains near a wall, but there's a much larger width of low density over here, and that's due to dilation. Now, so is this restricted to the cylindrical cuvette? And the answer is no. It's quite generic. So you take this slightly more complex flow. This is what's called the split bottom device. It was used to look at to study some aspects of kinematics of grains, and you shear the material by rotating a part of the lower of the base. Okay, so the base is split into two parts. The inner part rotates and the outer part is static, and so is the container. And this is the primary velocity profile. Okay, so the lower part, the part near the base, the grains near the base are rotating, and the rest of the grains are more or less static. And you get a secondary flow here. This is for a relatively tall column. Okay, so the fill height is about 1.28 times the radius of the rotating disk. And so you get a single vortex over here. Now, when you have a relatively short column, you no longer get a single vortex, you get two. But the point is, you do get this secondary flow, okay? And particles, again, it's nucleated by the region where there is shear, and particles fall down in the region of low density, okay? Now, this compares quite well with imaging experiments at the free surface, okay? So, the data points are what we measure, and these are for the short column, these data points, and this is the DEM measurements. These are our observations, data points, and these are DEM measurements. So, they are in agreement with experiments. Now, so now I come to my higher gradient theory that captures dilatancy. Hopefully, I would have convinced you by now that this is something that we need to worry about. We should try to capture dilatancy even at constant pressure. And the way we went about it is to now think about what really happens in a collection of grains when they are densely packed. Now, stress is not homogeneously transmitted. Most of us who study grains know that stress is transmitted along these force chains. So, there is local inhomogeneity, okay? And so, a local flow rule like this is probably not a good idea. If you want the deformation here, you would want to look at the stress or the yield condition in a small region around that point. That is the whole idea here. So, the flow rule is not local, the deformation rate is not determined by the yield condition at that point, whether the material is yielded there or not, but in a small volume around it. And that is the only physics here, there is nothing else. Once you do this, once you figure this out, then just a Taylor expansion is all you need. Okay, so I am going to use the simplest form of the yield condition, put it in here, and get my constitutive relation. Okay, so what I have done is I have a weighting function. So, this color over here indicates the weighting function. I only need to know two properties of the weighting function. It has to integrate to unity over the entire volume, and it has to have a finite size. Okay. So, once I have that, I put it in here and I Taylor expand. I Taylor expand this kernel, and that is what I get for the rate of deformation or strain rate. Okay. So, I have the regular the normal term, then I have a higher gradient term. Okay. The first gradient term is cancelled. So, I will use the simplest yield condition. Okay, I will not go into the details unless you are interested, and that is the form of the equation I get for the rate of deformation, both for the deviatoric part and the diagonal part. Okay. And the nice thing is, for the simple yield condition, I can invert both the two, and when I invert, I get a stress explicit relation, which we used to in fluid mechanics. Okay. So, the stress has a order 1 part and then a higher gradient part. The higher gradient part goes as the Laplacian of the strain rate. Okay. And this fluidity is simply the scalar invariant of the strain rate. All right. So, I am just repeating that here. Now, this is similar to what Joe Goddard proposed from his idea of dissipation potentials by including in the dissipation potential higher gradients in the velocity. Over here, I have not done anything, I did not need a dissipation potential, I simply assumed that you could volume average the flow rule. Okay. So, that is the only physics here. And so, what is important here is, now I can do the same thing for the isotropic part of the stress, and the pressure too has the normal part and a higher gradient part. So, the pressure has, the higher gradient part has two components, one that goes as the Laplacian of the solids fraction. I am sorry, I have switched the variables over here, nu here is the solids fraction, and there is the Laplacian of the divergence of u. Okay. So, it is just the Taylor expansion of the kernel. So all I've assumed is, to repeat, that I can volume average the flow rule around a small volume, and that's the true flow rule. Okay, the local flow rule is not what really represents the strain rate, is my thesis. So now if you simply look at this, at constant pressure you can now get a gradient in the volume fraction. Okay, that the system will allow that. So this is the so-called critical state pressure that will balance this term, and you can, in simple shear, get a balance and have the pressure remain a constant. Okay, now that's one part. Secondly, the theory is unconditionally Hadamard well posed. So I don't have to worry about ill posedness. I don't need to introduce an additional fluidity field which would have required boundary conditions which I had no control over, or I didn't know much information on. All the boundary conditions are required, and here's the connection to the Kosterow theory. The boundary conditions that are required are exactly what we used in the Kosterow theory. So here what you have is a slip velocity. Okay, the left hand side here is the slip velocity, for those of you who can see it. Right hand side depends on the particle spin, and n here is the unit normal to the surface. So I have the slip velocity comes from the particle spinning relative to the boundary. Okay, and there's a ratio between the shear stress at a boundary and the normal stress boundary that's constant. That's simply the wall stress condition, which is widely used in granular mechanics. And these are measurable quantities. I can measure the particle spin. I can measure the particle normal stress and the shear stress. So these are conditions I can test in the laboratory. I don't know of a way of measuring the fluidity, which was proposed by Ken Cameron and his co-workers. So this, I think, is more physically realistic, and importantly it captures constant pressure dilatancy. So let's see how it does. How many minutes do I have? Okay. How many minutes do I have? 5? Okay. Yeah. Great. Okay. You can't see anything here, but this is a repetition of what I showed you earlier. This is the density profile that we observed in this cylindrical cuvette device. Yeah, I'm really sorry. There's nothing I can do. I don't know what happened. So this was the density, the volume fraction as a function of the radial position from the inner cylinder in a small slice around here, in midway between the top and the bottom. Okay, and as you can see, the density increases, and then this is the density that was there when it was poured. So there's nothing much one can do about here because there's no flow. Now if I solve the equations, I get a velocity profile that's exponentially decaying, which, as I told you, it was in agreement with experiments, and I get a density profile that looks similar to that. So I do get an increase in density as I go from the wall away from it. Of course I don't get this crystallization induced order here, or sorry, reduction in density, but now let's look at a more complex flow. Okay, let's look at the split bottom cuvette. Rather than looking at a cylindrical split bottom cuvette, let's look at one where I have a rectilinear chamber in which half the base is moving with a velocity +1 and the other half with a velocity -1. Okay. Now that's the velocity field you will get. So your material is moving in the x direction. So this is a simple, the assumption is that all the flow is only in the x direction. So the secondary flow is not allowed here. But I do get a velocity field that resembles measurements in DEM, which you can't see. I'm sorry. So this is to show you that if I take slices of here, of this, you could measure that from DEM experiments, and these two will agree. Okay, and I can predict the density fall near the split. So what you're looking at is the vertical axis is the volume fraction, the y axis is the transverse direction here, and z is along in the flow direction. Okay. So right near the split there is a fall in density, and near the base, well, there are no measurements of that, so we'll have to confirm that later with experiments. But as you know, the real flow is more complex. It's not unidirectional. So there's a secondary flow even in a split, and so the question is, and the volume fraction is not just small at the split. There's a low volume fraction region all the way to the top. Yeah, I tested this about 5 minutes ago, or rather a couple of hours ago, and it seemed perfectly fine. There was nothing wrong with the presentation. Okay, so to conclude, I hope I would have convinced you, despite the poor quality of the slides, that dilatancy is a generic phenomenon, okay, and one should take it seriously. We have a good agreement between experiments in the split bottom cuvette device and our DEM simulations, and we have a non-local theory that has the potential of capturing constant pressure dilation, and therefore these kinds of secondary flows and non-trivial rheological effects. Thank you.
Questions? Okay, I'll go this way. Professor Goddard.
Dark, but oh, there we go. It's still a bit dark, so I can't see your facial expression, but so I don't know if you understand my question. So my question is related to the non-local theory. Can you say, so my basic understanding is that you do have this kind of length scale, similar to the other two theories that are proposed. You have the second derivative. You don't have a special fluidity parameter. So can you say a little bit more about what the strengths of your approach is compared to the two other approaches, and what you could, basically for me to better understand what the differences is.
So the length scale
differences are.
The length scale that you have in the fluidity model, both of, I've quoted Heron and Cameron, but there's another model by Bruno Andriotti and his group. Yeah? Yeah. But that's a little bit different, but they too introduce a length scale. And they don't need this evolution equation for the fluidity. The length scale is intrinsic. It's a property of the material. Yeah. That is something I have to characterize. I have to measure for each material. Yeah, that's right. So it is an intrinsic length scale.
Prabhu, it may be a question of, can you hear this all right?
Yes.
Question of terminology. Normally, I would use dilatancy to refer to the quasi-static regime having to do, as Reynolds told us, with particles riding up over one another. Yeah. And at large strains, we get the critical state where the dilatancy is zero.
Yes.
Now, as we crank up the inertia, we go into a compressible fluid regime. Right. So I'm having trouble deciding whether you're talking about compressibility effects at finite I, or whether you're talking about quasi-static flows.
Everything I've talked about is in the limit of 0I, or very small I.
Now,
right.
I think in defense of the granular fluidity guys, they freely admit that they're at critical state and they're not willing to take account of dilatancy because of that. They're in a steady regime, and their volume doesn't change. It's critical state. So that would be my defense of them.
Yeah.
They freely admit.
Yeah. Oh, that's a good question. So it's dissipative in that volume of radius L. It's not locally dissipative, but as long as you are. Yes, that's right. Yeah. But then, so it's self-consistent. I'm saying that strain rates are not locally dependent on the stress, but in the stress in that volume. And therefore, you have to allow me the luxury of making sure the dissipation in that volume is positive definite. Yeah.
Just a comment. I wanted to point out that there's a mechanism for dilation that you haven't mentioned, and that is anisotropy. If you have anisotropy at constant pressure, a shear strain can couple to a volume strain. And everything you've done has been, in effect, isotropic.
That's right. Yes, that's right. I assume that the material is isotropic. Thank you. Yeah. Yeah.
So, Prabhu, I didn't catch the part about if you introduce a curvature term, del squared, how would you not need additional boundary conditions?
I do. I need additional boundary conditions. So I thought I gave them. I need two in each. Let's say I have a boundary value problem. I have two boundaries. So I have two boundary conditions in each wall. But the point is these additional boundary conditions are measurable. I have a boundary condition for the slip velocity at the boundary. Okay, you could have no slip, but I have that boundary condition, and I have another condition which relates the shear and normal stresses at the boundary.
So these are boundary conditions that are come into account because of the term that you have added, or they were already there?
No. So I needed these in the Kosterow model, which was of the same order as this. But the Kosterow model, the physics was different. It required a coupled stress and a angular momentum balance. So I'm here assuming that the angular momentum balance is implicitly satisfied. I don't have to satisfy the angular momentum balance. But I still need these boundary conditions come in handy, is what I mentioned. Yeah.
Okay, question, Prabhu. So in the experiments that you conducted, if you had a top plate which did not allow the material to rise up, would you still have had the secondary flow?
Good question. It slightly suppresses it, but you always have a secondary flow.
And if I had no gravity, would I have a secondary flow?
No. So you need gravity. That's right.
And so then I want a question of philosophy for everybody in the room. In constructing constitutive models of things, in the granular flow, you're always doing the presence of gravity, which would seem to me to be something where you'd want to have a model where you didn't have gravity, and then you'd solve a flow problem with gravity in it.
So the solution I showed you in the end was without gravity, plane shear without gravity. You do have dilation. Gravity causes this secondary flow. You need shear and gravity both present and non-collinear. If shear and gravity are in the same direction, you don't see any secondary flows. So in other words, if I'm shearing material between two horizontal parallel plates, there is no secondary flow. But if they are not in the same direction, I always get it.
But couldn't you also have a normal stress-driven secondary flows?
Well,
could be another source of it instead of gravity?
Yes, I mean, that's a good question. I don't have the answer to that. I hope I have convinced you that dilatancy is what's responsible for this. But there are always normal stress differences. There are huge normal stress differences in granular materials. Okay, so that's always true. Yeah.
Any other question? Yeah.
Yeah. Yeah, that's right.
So, how you take into account?
So those kinds of loose packings are very hard to generate under gravity. Under gravity, you always get a packing which is near 60%, and so material always dilates when you shear it. But yes, one could conduct computer experiments by packing the material very loosely, and we finally reach the same steady state. So the plasticity, critical state plasticity theories are valid. Yeah.
Any other questions? Okay, last question.
So you said the length scale L is typically the region within which your entire dissipation occurs. That's one way, at least that's
I answered Joe's question by saying that the same volume that I averaged over to get the constitutive relation. Within that volume, the dissipation is positive. But the dissipation is not positive locally everywhere.
I see.
And that length scale is a property of the material. It's not something you specify, that you have the luxury of specifying.
I see. And what
So
is
for
that
sand,
typical-
it would be say 10 particle diameters.
10
For rice grains, it would be 5 or something like that.
I see.
Yeah, typically for elongated particles, it's smaller.
Okay.
Okay, so please join me in thanking the speaker.